Hello students, welcome to the first session of our first module in the subject Mechanics of Solids, MOS. So students, in the previous sessions we have studied the basics about stress, strain and the relationship between stress and strain, how a body how a body deforms when tensile or compressive or shear force acts on it, how internal forces are generated to encounter the effect of all these things, how a body is getting strained. So all these things studied. But students, in the previous session we have dealt with very simple type of loading, right? No complex loading. Suppose this is a rod of uniform cross section. This is a tensile force of F unit magnitude F. Okay, so this type of loading is an uniaxial loading on a very simple rod. Simple rod in the sense it is having a uniform cross section. So it is very easy to find the stress in these cases, because since this is uniform, its area is, suppose this area is A, so this area is constant at any cross section, 1 1 or 2 2, at any cross section area is same. So this is considered to be a simple object or simple structural member, uh, which is having a single loading. Okay, so in actual cases, suppose in a structural member or a machine element will not possess such uniform geometry, uniform geometry, not possible, not possible in actual cases. Suppose various, suppose in an automobile engine, or in an automobile crankshaft, or a piston inside an engine cylinder, or an aircraft wing. All those things are not having a simple geometry, not simple geometry. They are having a complex geometry, so they don't have an uniform cross section, and also they are not subjected to loadings, and a uniaxial loading or simple kind of loading. They are subjected to both complex loadings. Sometimes they are even dynamic too, right? Dynamic means they are changing with respect to time. So we don't consider here dynamic loading in this subject. We are more interested in static loading only. So suppose, for example, I'm writing this like crankshaft, crankshaft, right? Or aircraft wing, and like a piston and engine cylinder. So what are the peculiarities for all these kinds of structural members or machine elements? What are the peculiarities they are having? They have complex geometry, complex geometry, and complex loading too. So geometry is also complex. Force applied, the loading, load means force. Applied forces are also complex. They are not as simple as that. As simple as those things, those figures, or those situations we have studied in the previous sessions. I will draw a. Suppose this is an element, some spherical, not spherical exactly in shape, an element. Suppose this is having so much of loading, like some F1 force here, F2 force here, some F3 force here, some uniform kind of loading P here, uniform loading, right? And some some reaction from supports. Here one support, here another support. So naturally there will be reaction forces R, R1, R2. Okay. So this element is subjected to numerous subject to a very complex loading. So how can we find a stress in this? Suppose this is a section I have taken. Okay, one. How can you calculate stress in this particular object? Can you apply the theories you have studied in the previous sessions? I taught you in previous three videos. I taught you how to calculate stress. Stress is nothing but internal force or resistant force divided by area. So can you calculate the internal force, or can you calculate stress based on resistant force and area? No, because since these forces are acting in different directions, they are not at least they are not uniaxial. They are not equal and opposite. Okay, they are not point loads. Some are point loads, some are uniformly varying loads. Uniformly distributed loads and uniformly varying loads. You have studied in engineering mechanics, right? So some are reaction forces. They are not concurrent. Some are not. Uh, Means these acting loads are complex loading, right? So we are not able to we can never calculate stress based on the theories we have studied in the previous sessions. Okay, so how will you calculate stress? So students, I have a body here, and here this is a body subjected to complex loading. So this geometry is also complex, loading is also complex. There is some point loads like F1, F2, and reaction load, and F3, and reaction load R1, support reaction R1, and uniform loading of P. Suppose I am taking a point P, particular point P, anyway, with the coordinates x, y, z in that particular body. Okay, so I am taking a plane 1 1 to cut this into two sections. I am applying method of sections here to make two sections. So I will have two sections, C and D, right? C and D. So P will have P on D, and the same point P on the counterpart on that counterpart of the same point on the section C, P dash. So P and P dash are same, but the coordinates are same, but now we are drawing it in two separate free body diagram for two sections C and D, right? So P be a point inside the body with coordinates x, y, z. Let the body be cut into two parts C and D by a plane 1 1 passing through point P. So if we consider the free body diagrams of C and D, okay, then each part should be in equilibrium. So initially this whole body was in equilibrium. So even if we are cutting this body into two different sections C and D, then each part should be in equilibrium under the action of externally applied forces. And how this externally, so how this C will be in equilibrium? In order to remain C in equilibrium, there should be an internal force. Suppose this here acting through point P, an internal force is acting. Suppose it be, I am naming it as some delta T. So delta T acting through P dash is maintaining the whole body C in equilibrium. Similarly, for this D to be in equilibrium, another internal force through P delta T dash. So let this be t dash, then let this be delta t. So this direction, the direction of this delta t should be opposite. Magnitude should be equal to this delta t dash. Delta t delta t dash should be equal to delta t, but opposite in direction, right? You can see here delta t in this direction, delta t dash in this direction. Okay, so this delta t dash make this internal force delta t dash make this portion C in equilibrium. This delta t makes this portion D in equilibrium. So delta t and delta t dash are the forces, internal forces at the point P, right? Right. So how to find the stress at point P? If you have to find stress, we have to take a small area. I will show you. Small area, small area around P, small area around P dash, and small area around P. Let that area be delta A. Delta A. Okay. Both area be you should take both area same delta A. So students, since P is a point, we cannot take delta A as a having. We cannot assume that delta A having a finite magnitude. So delta A should tend to 0, right? Since P is point. So since P is a point, P is a point, delta A should tends to 0, right? 0. Okay. Now therefore we have to stress will be equal to limit A tend to 0 delta T by delta A. Okay, equal to either dt by, so limit delta A tends to 0 means d by dA of t. So this will be some t vector. So this is known as stress. So delta t was the force, t1 t vector is the, let it be t vector. T vector is a stress. The stress is actually a vector here. Okay, stress is vector. Similarly, so this was the case of section C. Similarly for section that was for section D. For section C, limit delta A tends to 0 delta T dash by delta A, right? So it will be equal to d by dA of t dash equal to t vector dash. So this is stress on the section C. So section C and section D are having. So what should be the condition? The vectors T should be equal to magnitude but opposite in direction. Right? Right? They should be equal and opposite in magnitude and opposite in direction. Right? So I will draw once more. So here t vector, stress vector t dash in this direction. Similarly on the lower portion it should be equal but opposite in direction. So t vector should be equal to t dash vector minus. So students, this was based on an arbitrary plane I have chosen for point P dash and P, same point P. I have chosen an arbitrary section 1 1, but 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 if I have chosen another plane some 2 2, this will become C and some 2 section E and F. Same loading like F1, P, F2, F3, R1. But here if I take another point, same point for the same point P dash P, but I have chosen another plane. Instead of 1 1, I have chosen 2 2. So 2 2 is having another orientation, different orientation. So what will happen? So what will happen? So sometimes this may have a stress at the same point P. This may have another what another stress here. Another stress with a different direction. Suppose this be T2 vector. I will draw with another color. Suppose the same point P, same point P, different plane. So this is having some T2, vector T2. Students, suppose the same body with the same loading, and we are taking the same point P, but we are cutting cutting the body through the same point P with a different plane, 2 2, plane 2 2. Okay, with a different orientation, different from the initial plane 1 1. So what will happen? The same through the same point P, some internal force may act, but the direction and the magnitude may be different from. So delta T2, delta T2 and delta T2 dash. So both are equal and opposite direction. So both are equal, but act in a opposite direction, right? So these are the internal forces in this case, but in the previous case it was delta T and delta T dash. So these are different from, they are not equal, they are not either equal in magnitude, not equal in, nor equal in what the direction, right? So here we can calculate stress. If we are taking a small area, stress may be some vector T2 vector and minus T2 vector dash. So they are equal but opposite in direction, right? So students, what are you inferring from these two cases? So we have studied two different cases, same body, same loading, same point, but two different plane. So what do you understand from these two cases? So initially the body, I will show you another case. Same body, but another point Q dash Q, same loading, here sometimes, here the internal force will be some delta T3 dash and delta T3, right? So what do you infer? you will understand that, you will understand that stress at a point, stress at a point will depends on what all things, depends on not only on the location, of that point. So initially P was some x, y, z. Later I took a Q with different x1, y1, z1. So two different point has got two different stress acting on that point. So stress at a point depends not only on the location of point, but also on another factor. What is the factor? But also on plane passing through that point. Plane passing through the point. So very important, two factors depends on location and plane passing through the point. So in order to identify so a plane can be identified using a plane can be identified or named by using the direction of cosines nx, ny, nz of the outward normal to that particular plane. So students, have you studied the concept called direction of cosines? Maybe you have studied, you might have studied in your previous mathematics class. I hope you have studied. If you don't know the idea of direction of cosines, please check it on your own, or you can contact your mathematics teacher. So I will show you what actually. So suppose I am having a plane. This is my plane, and this is the outward normal n vector. So n vector. So this n vector will have three components called nx, ny, nz. So these components are direction of cosines. This students, this is our plane and this is our outward normal to that particular plane. Then we can resolve this n vector into three: nx, ny, nz. So these components are called directions of cosine. So if we know the value of nx, ny, nz, before us we have the values nx, ny, nz. So using these values we can identify the particular plane. So nx, the value will be specific to each particular plane. So students, I will show you what actually, suppose this is our Cartesian plane, like this Vy, X, Z. Suppose this is origin, and this point to this point the n vector is a three-dimensional n vector is acting in this direction. Suppose it is having a angle alpha with x, some gamma with z, right, and some beta with y. So nx is nothing but cos alpha, ny is nothing but cos beta, nz equal to cos gamma. Okay, so that's how that is what cosine, uh, what direction of cosines means, and there are various properties. Actually, nx can be, suppose if you don't know the, if you don't know if you don't know the value of angle, but you know the coordinate of this n vector, x, y, z. N vector, the that particular point is x, y, z, means x, y, z, means this is x, this is z, and some, this is y. So their coordinates, so these coordinates are known, right? Suppose you know the coordinates, then cos, or sorry, nx can be calculated by nx, can be calculated by x by root of x square plus y square plus z square, ny y by root x square plus y square plus z square. Similarly, nz equal to z by root x square plus y square plus z square. So students, if you add nx square plus ny square plus nz square, it should be 1. So these properties you should know. I'm just briefing these ideas. This is you should have known these concepts even before entering to this semester. Okay, so I believe you have already studied in these things in your previous mathematics classes. So don't worry, we will be doing some problems. Then you will get. If you don't have any idea, you will get, okay, more. Uh, these concepts will be more understood when you are doing problems. Okay. So now we have studied the stress at a point. The stress at a point depends not only on the location, but also plane. So plane can be identified using directions of cosine nx, ny, nz. Okay. So the state of a stress at a point. State of a stress at a point. So what is the importance of state of a stress at a point? Because we have we may have infinite number of planes. Infinite number of planes. Infinite number of planes which can be drawn through a point. So we get an infinite number of stress vectors, right? So we have studied that if we are taking a particular point on a particular body with a particular location, the stress vectors vary. They vary with the plane we are selecting. So since we can draw infinite number of planes through that particular point, we can have infinite number of stress vectors acting at that given point. So each stress vectors are characterized by the corresponding plane on which it is acting, right? So the totality of all stress vectors, the totality, infinite stress vectors at a given point. Why? Why? Because we can have infinite number of planes through a given point. So each plane will have a particular stress vector. So the totality totality of all stress vectors acting on every possible plane passing through that particular point is defined to be the state of stress at that point. Okay, totality of all possible stress vector, all stress vectors uh, vectors acting on every possible plane, every possible plane passing through the point, passing through the point, passing through the point is defined to be what? Is defined to be what? State of stress. State of stress at that point. At that point. So students, very important. What is state of stress at that point? It is the totality of all stress vectors acting on every possible plane passing through that point. Is defined to be the state of stress at that point. So students, we in the previous sessions we have calculated, or our idea of stress was something acting on a plane, but now we have improved our knowledge on the stress, or we have changed that perspective of stress to another perspective, that stress is nothing. Stress is not acting on a plane, but it actually acts on a particular point. So stress acting on a plane means it is the integrated version of all the stress that are acting on points that are part of that particular plane. So that plane may consist of different points. So different points will culminate together to form that area. So the stresses acting on each point culminate together to get the total stress acting on that plane. So that's the idea. Okay. So it is very important that to understand that we cannot calculate stress on a plane directly in case of a complex geometry and complex loading. So we have to go for finding stress at a point. Okay, so that's the importance of state of stress at a particular point. So are you getting? Suppose I am having a body, a section of a body, right? I am calculating. I have taken a plane, a section such that the plane is having a normal vector n vector in this direction. Suppose the stress is acting in another direction. Suppose the n vector, since this should be a vector, I am putting n. I am putting n because this plane is having an n vector, normal vector with a name n. Okay. Suppose this stress vector can be resolved in two ways. First, I am resolving this stress vector, one in this direction, the direction of normal, and another direction perpendicular to normal. So Tn vector resolved in two directions. First in direction direction of n vector, and another is perpendicular to n vector. So the component of Tn in the same direction of n vector is the normal stress factor. Okay, normal stress factor. I will show in this way. And perpendicular to n vector is tau n, shear stress factor, shear stress component. So this is sigma n. So this is tau n. So the stress acting perpendicular so sigma n is acting perpendicular to the plane. So that is why perpendicular to the plane means it is parallel to the outward normal. So that is why that component is known as normal component. So tau n is acting parallel to the plane or perpendicular to the outward normal. So this is known as shear component. Okay. So we can write Tn vector, the magnitude of Tn vector, magnitude square of Tn vector will be nothing but sigma n square plus tau n square, because these are its rectangular components, the perpendicular components, right? Perpendicular components. So we can have two components for a stress vector at a point. One is normal component, another is shear component. Shear component is tangential or parallel to the surface. Normal component is perpendicular to the surface. So these ideas you have already learned in previous sessions, right? Because in case of perpendicular, we have studied in that case like this. So here we will have normal stress. In this kind of force we will have shear stress, right? So that is how we learned in a simple with a simple geometry and simple loading. But in complex loading, this is how we define normal and shear stress components. So another method of resolving this, suppose I am having the same body with same outward normal with the same stress component Tn vector. Suppose this is our Cartesian coordinate, like this is y, x, z. So this T can be resolved in along these three directions also, right? Suppose parallel to Tz, some Tnz, parallel to x, some Tnx, parallel to y, some Tyn. So Tn can be resolved in these three rectangular coordinates or Cartesian coordinates also. So in this case we can write the Tn vector square will be equal to what? Txn square plus Tyn square plus Tzn square. So either way we can write, we can resolve in both ways. This is one way, this is another way, two way. Here we are resolving it into normal stress and shear stress. Here we are resolving based on the direction of the Cartesian coordinate system. So the Cartesian coordinate system, suppose we are having section like this. This plane is parallel to x. Actually xy plane, if xy plane is actually same as that of the plane we are taking, and our normal vector n is parallel to z, then both kind of resolving will be same in this case. But this is our plane, Cartesian plane, and we are taking a plane in this direction like n vector. This n vector is neither parallel to any of the Cartesian xyz nor perpendicular to any of the xyz. In such cases, both resolving will be different from each other. Oh, are you getting? Are you understanding these points? So if you have any doubts, we can have a Google Meet session. We can discuss it. We can discuss it from the beginning itself. Don't worry. Okay. Suppose students, this is our Cartesian coordinate. This is x, y. Sorry, this can be z, y. Okay. So I am trying to teach you how we define a particular plane perpendicular to each different direction. Suppose I am taking a plane in this xz plane. So this plane will have a perpendicular n vector parallel to x, right? So this plane is called x plane. So any plane having an outward normal parallel to x-axis means x plane. Okay. Suppose I am taking another plane like this. So this plane is in xy. This is an xy plane, right? It is having a normal vector n vector parallel to z. So this plane is known as z plane. So any plane having a normal vector parallel to z axis is z plane, and now x z y. So what will be this plane? Plane in this direction which is having a normal n vector parallel to y. So this will be y plane. Okay, so students, you should always remember what actually is explained when in our proceeding sections. I will often use the terms called explain, y plane, z plane. So things should be understood to you. What actually is explained, what actually is y plane, what actually is z plane. So x plane is nothing but plane having a normal parallel to x axis. Similarly, y plane parallel to y axis, z plane normal parallel to z axis. Okay. So students, this is our coordinate system. Okay. Okay, I am taking z here, y here, x here. I am having a body. Okay. Suppose I am cutting this body with a plane, an x plane, because outward normal is parallel to x. Okay. So what will happen? So this body will be cut in an x plane. So the normal to this plane n vector will be parallel to x direction, right? So this will be x plane, cut in x plane. Okay. Suppose the n vector is like this. Suppose a point P is taken. Let the stress acting at that point. Suppose it is having numerous force loading. Okay, F1 or F2. So naturally there will be a stress. So since the direction stress is like this, okay, now I can resolve this stress vector. This is stress vector in three directions, like x, z, y, right? We have already studied how to resolve. So if I am resolving this in x direction, y direction, z direction, three different directions. Okay. So I'm naming this. So any component parallel to n vector will be naturally what it will be, a normal component. So it can be defined as sigma. Since sigma is acting on x plane, I will write it x in the direction x only. Sigma is x. since this first subscript represent the plane through which it acts, the plane used to cut that element. So here we are using x plane. Next subscript represent the direction of the stress. Since it is acting in x direction itself, it is called sigma xx. Now here this component is parallel, actually parallel to the surface, right? Our surface is x plane, right? It's an x plane. This component is acting in z direction, this component is acting in y direction, this component is acting in x direction, right? So x direction coincides with the normal vector, so this is a normal stress, normal stress. Here this component is parallel to the parallel to the plane or tangential to the plane. So naturally what will be this component? This will be a shear component. How will you notate this? Actually, which is the first subscript will be the plane through which it depicts the plane through which it acts. So this, since this is acting in x plane, tau x direction is z direction, z direction. So this is tau x. Now what will be this one? Here also it is acting tangential to the plane, so naturally tau x plane direction y, tau xy. So students, I will draw it once more. Okay, so this was the point P, plane was x plane. Okay, normal n vector in direction of x only, same direction. Okay, this was our t vector. Okay, so t vector can be resolved into three components. First one sigma xx, second one tau x, this is okay, this is z, this is y, this was tau xz, so this is tau xy. Okay, and now students, I am taking the same coordinates, same point, actually same point P here, but I am cutting with a plane parallel is x, y, z. I am cutting with a plane having normal vector parallel to y. So this is a y plane, right? Normal n vector is parallel to y. So this plane will be y plane. So same point but different plane. Okay. So plane is y plane. N vector here in this direction, same point. Okay, so this is y, z, x. So here the since the plane is different, the acting t vector will be a different one. Let it be ty vector. So here also we can resolve this into three components. So one in y direction, one in x direction, one in z direction. So what will be this component? This component, since this component is parallel to n vector, this will be sigma itself, normal component, and depicted by y, because it is acting in y plane in y direction. This is tau acting in y plane in x direction. This is tau acting in y plane in z direction. Okay. Similarly, same point, another plane means a plane parallel to this one. Okay, cut like this. I will show. Okay, in this plane is y, z, x. So normally is in this direction parallel to z. So this is z plane, right? So we can have if this is having a stress component like stress vector z, so that can be, this can be resolved in y direction, x direction, z direction. So what will be z direction is like this, z direction, x direction, y direction, right? So what will be this component? This component will be sigma acting in z plane in z direction. This is tau zx. This is tau zy. So students, if we are having at any point P, one can draw three mutually perpendicular. Okay. At any point we can draw at least we can draw infinite number of planes, but mainly we can draw three mutually perpendicular plane, right? X plane, y plane, z plane, right? So naturally we can have three components in each case for stress acting at that particular point P, right? So what are the components? So we can have sigma xx, tau xy, tau xz. Similarly for y plane, sigma yy, sorry, before that tau yx, tau yz, sigma zz, tau zx, tau zy. So we can have at least nine components. These components are acting on three mutually perpendicular planes: x plane, y plane, z plane. Alright. So these components can be actually represented in a matrix form. The students note that stress at a point in matrix form. So this matrix form is nothing but stress tensor. Actually we write matrix form in this way: sigma xx, tau xy, tau xz, and here sigma yy, and here sigma zz. Okay, so here tau xy, here tau xz, sorry, tau yx, tau yx, here tau yz, here tau zx, tau zy. So this is how we write the stress at a point in matrix form. Stress at a point in matrix form. Stress matrix. This is the stress matrix. So students, I will show you. So this is the method to write a stress tensor or the stress in the form of matrix. Tau ij equal to matrix sigma xs, tau xy, tau xz, tau yx, sigma yy. So this normal component should be in diagonal. Normal components should be in diagonal. All other things are shear components only. Okay. So that is how we write it. So tau ij is the stress component. Stress ij, I and j varies. It may be x or y. So when tau ii means a normal component, tau ij is shear component. Because if the subscript are same, it means normal component because it is acting in the same plane in the same direction. If it is acting in x plane in x direction, that is the normal component only. Okay, so that's the idea. Now, students, suppose we have the same body P in x, y is that Cartesian coordinate. We are having the same body at the same point P. So suppose we are supposed to find the stress, the components of stress at a plane, an arbitrary plane, which is not x y z. Not it does not get is not included as either x, y, or z. Here we are selecting some arbitrary planes. Suppose a plane in this direction. So this is neither x nor y nor z. So, but this plane is having a normal vector n vector with the direction of cosine nx, ny, nz. So these values you know. So these values you know the plane. It is not x plane, it is not y plane, it is not z plane. So you cannot use the stress tensor like sigma x, tau x, y, tau x. Such a stress tensor cannot be used in this case. That can be used only in rectangular coordinates. If the plane is x, y, or z. So if you are asked to find the stress at a stress in a point based on a particular an arbitrary plane with the direction of cosine nx, ny, nz, what will you do? So here you should apply the Cauchy's equation, Cauchy's equations, Cauchy's transformation. So you don't have to worry about the derivation of the equation. No derivation required. No derivation required, because you will study the derivation in your higher classes, maybe in AMOS, Advanced Mechanics of Solids and all. So as of now, you don't worry about the derivation. No derivation required. Okay. So how will you apply Cauchy's equation? I will show you. So our problem was like this: the body P, an arbitrary plane. So this was x, y, z. Okay. So the normal vector is n vector. Nx, ny, nz are the direction of cosines. Suppose the stress is acting like this. So this is the stress acting t vector n, or t vector. Okay, t vector. So we don't know t vector. We don't know the direction. How to find the components of this t vector, or we don't know how t vector is acting. But if you know the if you know the stress component, the stress tensor at P, that is tau ij equal to sigma xx, tau xy, tau xz, tau ix, sigma yy, tau yz, tau zx, tau zy, sigma zz. So if we know at point P, if this thing is known, and you know this thing also, so you can calculate the component of this t vector in x direction, in y direction, in z direction using Cauchy's equation. How? The Cauchy's equation is like this: sigma xx, tau xy, tau xz, sigma yy, sigma zz, tau yx, tau yz, tau zx, tau zy. This matrix into direction of cosine nx, ny, nz will give you the component of stress vector in x direction, in y direction, in z direction for that particular plane. So this is called Cauchy's equation. So you can this is the way to calculate the. So how you can expand this matrix? How? So tau x is nothing but nx sigma xx plus ny tau xy, right? Nx tau xy plus nz tau xz. So ty equal to nx tau xz xy plus ny sigma yy plus nz tau yz or zy. Tau z equal to nx tau zx plus ny tau zy plus nz sigma zz. So these are the three equations, Cauchy's equation. So earlier we have written in matrix form, now I have written in algebraic equation form itself. So if we know these values, all these values, you can calculate this stress tensor. What is this stress tensor? Suppose this is our body. We are having a plane. We are supposed to calculate the component of our stress at this point. The normal is like this with nx, ny, nz the direction of cosines. Okay. So you should calculate this t vector for this particular plane, for this particular point. But you know the point, the stress tensor based on the rectangular coordinate system for this particular point. So if you know that, and if you know this nx, ny, and z, we can calculate the component of this along tx, along y, dy, along z, tz. If you know all the components, then t vector is nothing but the magnitude of t vector square will be equal to what? Tx square plus ty square plus tz square. So tx, ty, tz should be calculated first, then sum of their squares will give you the magnitude, the square of that magnitude of the total vector. Or t vector, magnitude of t vector will be equal to tx square plus ty square plus tz square. Okay. So that's how. And if sigma n and tau n corresponding to that particular stress component should be if is to be found, what will you do? We know that t vector square should be equal to sigma n square plus tau n square. Right? So what is sigma n square in this case? So this is our body, this is our plane, this is our point. So this is our normal vector. This was our t vector. T vector is already found by square root of tx square plus ty square plus tz square. So the component of this t, along this n vector is sigma n. Perpendicular to that n vector is tau n. So this is different from sigma xx, sigma yy, sigma zz. Sigma xx is parallel to x, sigma yy is parallel to y, sigma zz. Here this sigma n is parallel to this n vector. Okay, so that's the difference. So how can we find sigma n and tau n for? So sigma n can be found using the equation nx nx of tau x plus ny, sorry, ty, tx, ty plus nz, tz. So this is how we find the normal component of. So if normal component is known, t vector whole square will be equal to sigma n square plus tau n square, right? Since this is known and this is also known, then naturally we can find this, right? Because tau n square will be this square minus this square. So this is how we find various stress components at a point based on Cauchy's equation. So hope you have understood these concepts. If you are not able to follow these concepts, we can have one more class through this platform, maybe through Google Meet. As I have already told you, we can have a discussion of the things we have already covered in this four sessions, including this session. We can have a discussion once more, and I will try my level best to make things clear to you in those sessions. Okay, thank you. As I will stop this session. Thank you.